Hello, my name is Justin Qualley, and during this presentation I will explain my contributions to the drone video research team for this semester. The problem that we are trying to solve is to capture, label, and annotate video recorded from a drone in order to create a dataset that can be used to test solutions performing segmentation and person re-identification. We also are working on creating metrics to compare and measure the accuracy and power usage of solutions to eventually create an infrastructure for teams to compete and accelerate progress. Person identification is defined as the problem of being able to detect a person and then, after that person has left and returned to the view of the camera, recognize this as the same person seen previously. This is a hard problem for computers to perform because it is more than just object detection. The computer must be able to store a memory of each unique person and then be able to know when that same person is seen despite varying changes in how that person might look at a different point in time. This is shown as the image on the left, where each person is drawn in a bounding box and labeled with a specific number. Segmentation is defined as the problem in which every pixel in an image is given a label as to the identity of what object that pixel makes up in the image. In other words, each object is filled in, pixel by pixel, to its exact dimensions. This is a difficult computer vision problem because it takes a large amount of processing power to extract features from images and accurately assign each pixel a label. Also, it is difficult to segment and identify humans because their body positions change so dramatically. The reasoning behind creating a dataset for drone video is that first, there is no existing dataset for drones for both segmentation and person identification. Also, the deployment of autonomous drones has become a critical future goal of the logistics, shipping, and healthcare fields for improved labor and health services efficiency. In shipping and logistical applications, autonomous drones can significantly reduce emissions over trucks in low-volume, low-radius delivery locations. For example, Amazon has tested delivering small packages using the drones pictured above. Additionally, autonomous drones in the emergency healthcare services field can be used for automated external defibrillator delivery, which can reduce out-of-hospital cardiac arrests. For these implementations of autonomous drones, the drones must be capable of performing both person segmentation and person re-identification. This is necessary for improvements in the safety of autonomous drones to reduce current legal restrictions on the deployment of autonomous drones in warehouses and production facilities for logistics and residential areas. We also have decided that the altitude required for our dataset to be useful for person re-identification is between 2 to 3 stories, so all sequences will be filmed within this range. Next, we will be moving on to my contributions during the semester. My first contributions came in the form of ideas that I made the team aware of through my reading of many research papers. Of these research papers, here are the most notable. First, Aligned Re-ID, Surpassing Human-Level Performance in Person Re-Identification. This paper presents a novel way for performing person re-identification that was so accurate when trained on the Market 1501 dataset that it scored higher than humans for re-identification accuracy. The method they propose extracts a global feature from a cropped image of a person and then extracts local features for each region of the image shown above. Then, between two images, the regions are realigned, distance calculated, and re-identification is performed based on the smallest possible distance. For example, shown above is a visual illustration of this method. Regions 1, 2, 3, and 4 of the first image correspond to only region 4 of the second, as that is where the man's head is. And this pattern continues down, matching the regions that make up his shirt, legs, and feet. From this paper, I suggest that we modify our video sequences to be inputted into Aligned Re-ID, and then integrate the output of matched persons into whatever video annotation tool we use, so that person can be automatically re-identified and labeled. The next paper then was titled Dynamic Video Segmentation Network. This paper presents a method for automatic video annotation in which the task was divided among two convolutional neural networks, a shallower CNN that segments portions of the video that are not changing significantly, and a deeper CNN that segments portions of the video that are changing. By splitting this process into two networks, the segmentation is performed faster and requires less processing power, which aligns with our goal for high-efficiency, low-power solutions. So I suggested that we implement this solution to our video sequences to automatically segment the people, which will be the constantly changing objects. From these ideas that I suggested, I also developed a roadmap for solving the problem of automatic video annotation, specifically related to person re-identification. Here shows the 4 main steps of this plan. First is to install and experiment with CVAT, a powerful video annotation tool I will discuss more later in this presentation, and Aligned Re-ID. Now, I have already performed this step, and shown here is my initial progress working with aligned re-ID and attempting to apply it to our dataset. I downloaded the Market 1501 dataset and all the code that comprises aligned re-ID, and I ran it on the Market 1501 dataset. Shown above is my laptop's terminal as the solution ran. As you can see, the metrics for measuring the accuracy of re-identification are mean for precision, MAP, and CMC 1, 5, and 10. The MAP score of 85.97% means that the algorithm was correct in its re-identification of people for 85.97% of the times that it performed re-identification. The CMC1 score means that 89.95% of the first choices for a match were correct, and CMC5 means by the fifth choice 94.54% of matches were correct. The next step then is to convert the video sequences that we have into the same format as the Market 1501 dataset so that aligned re-ID can be applied to our dataset. One method of doing this is to take one frame before and after a person leaves and then cut out each person from these frames and save them as their own image. Shown here, the Market 1501 dataset includes thousands of images in the same cropped format shown on the left. On the right is the desired format of our dataset taken from a draft video sequence. The times that a person leaves and returns will have to be documented and manually entered into the algorithm by a human annotator so that aligned re-ID knows when it is supposed to perform person re-identification. The next step then is to research as to how aligned re-ID knows what identities to look for so that we can replace them with the identities of the people in our video sequences instead of those from the Market 1501 dataset. Finally then, we must integrate the output of these matched images from aligned re-ID into CVAT, the computer video annotation tool, so that it can be automatically annotated. I was making progress in this plan until recently our drone video team partnered with the crowdsourcing team, in which the responsibility of creating methods for automatic annotation has shifted to becoming theirs, and our team is now focusing on the design and capture of our dataset and the creation of competition metrics. Moving on, I also made contributions in solving the problem of person segmentation. I did this by exploring a color segmentation algorithm called K-means. This algorithm segments colors by creating a plot of every pixel in an image and then assigning each point on the plot to a specific K number of clusters. It then reassigns a centroid to each cluster until distance is maximized. Every pixel in a cluster is then assigned the same color, essentially removing any small variations in color, filling in the image, and segmenting it. This animation shows this process happening based on 4 clusters. As you can see, in this example, there are 4 colors: blue, green, red, and orange. And the clusters move after they have been assigned to each of the pixels. I then applied this algorithm using Python to the frame of our initial draft video sequence, and this was the result. I set K equal to 3, and as you can see, there are 3 main colors in the image on the right: light tan, gray, and dark brown. Also, you can see how the image looks more filled in and there's less variation in color. After doing more research into the K-means algorithm, I learned that it has many weaknesses that make it not useful for our purposes, but I believe there was value in working with this algorithm as a way to become more familiar with working with the data structure of images. Another contribution I made this semester is suggesting and designing sequences that include a variety of human body positions. It was evident from the research papers I read that one of the main challenges of person re-identification is being able to recognize a person when the shape of their body is different than previously seen. For example, without my sequence designs, most of the other sequences the team has designed would look like the image on the left, in which every person is upright and walking. And then when they return to the frame, they are the same. But in order to make a useful testing dataset, we need to simulate a variety of natural occurrences. So this includes alternate body positions, like a person sitting down or laying down as shown in the second image. Specifically, the sequences I designed include a person running in and out of frame, and a person sitting, standing, leaving, and then returning to the frame. Now, moving on to the sequences I designed. Starting with the simplest one, this sequence was designed with the guidelines that all persons have muted clothing, do not include each other, and 3 people must be re-identified. So as you can see, the sequence is diagrammed in a 2-minute loop, which will be repeated 2 times for a total of 4 minutes. During the sequence, person 1, 2, and 3 move slowly forward while persons 4, 5, and 6 move perpendicular to them, eventually leaving the frame and returning at staggered intervals. Also, the drone will move backwards in the same direction as persons 1, 2, and 3 to ensure they remain in the frame the whole time. The next sequence I designed is a little more complicated. In this sequence, all persons in the frame must be re-identified. There is a mix between bright and muted colors, and every person in the frame is included at least once. As you can see, persons 2 and 4 move diagonally, including each other in the middle, and then leave after 20 seconds. Then, persons 1 and 5 move in the same pattern and leave the frame at 30 seconds. Finally, persons 3 and 6 move diagonally, including each other twice, before they leave the frame at 60 seconds. All persons then return to the frame 30 seconds after they have exited, and this process is repeated 3 times for a total of 4 minutes and 30 seconds. The final sequence that I designed is one that the team decided to add later on in order to more extensively cover real-world scenarios. The main idea of this sequence is that the drone moves upwards to reveal persons that have moved out of the frame and returned at a different elevation than they started. The sequence functions the same way as previously described sequences, except the movement patterns of persons 3 and 6 are changed. Person 3 leaves the frame at 20 seconds and returns after 40 seconds on the second floor, then walks forward until they exit the frame. Person 3 leaves the frame after 60 seconds, then returns 30 seconds later on the second floor and walks forward until they exit the frame. During this semester, I also researched available tools to assist in the process of video annotation. I first looked into VADIC, pictured on the left, which appeared to be a promising tool from the sample footage I found. The annotator was able to draw bounding boxes quickly and assign specific labels to each object frame by frame. Unfortunately, there was no download available for this tool online, so we were not able to use it. Next, I looked into Viper as I had seen it referenced in many papers. I downloaded it and followed the installation instructions and attempted to annotate one of our draft sequences. But the user interface felt hard to use, and there was no way to perform automatic annotation. We would have to build those algorithms ourselves. Finally, I worked with CVAT, the computer video annotation tool created by a team of dedicated developers at Intel. This was the most promising and most powerful tool of the three. The user interface was friendly, and it was easy to upload videos to be annotated. The tool functioned in much the same way as VADIC, as it allows an annotator to draw bounding boxes very quickly around objects using a crosshair. But the main feature of CVAT that sets it apart is its ability to interpolate between frames, drawing bounding boxes between manually annotated keyframes. This makes it much faster for annotating video, as you don't have to manually annotate each frame. The weakness of this tool, however, is it only interpolates and draws bounding boxes through Euclidean distance and velocity predictions. This means that the bounding box does not change as a person's legs or arms swing forward, and it does not track properly if a person makes a sudden movement. This can be remedied by drawing more keyframes and adjusting the box width, but it is not an ideal solution. Moving on, I also made contributions to the team by participating in draft video sequences and filming them. Pictured on the left is our original draft video sequence that we took at the beginning of the semester to experiment with ways to automatically annotate video. They were filmed with my iPhone X camera, and I filmed from the second floor walkway in Armstrong to better simulate the video as if it were taken by drone. Next, pictured on the right, is a screenshot of the most recent draft video that I participated in for the crowdsourcing team to experiment with annotation solutions. We performed a modified version of my sequence, which was a little bit more simple, in which two people stay in the frame at all times, sit at a table, and when one person leaves the table, then returns. This was filmed with the drone camera, but the drone was held and carried across the second floor walkway in order to simulate drone video because we were not authorized to fly indoors. I also contributed by providing input for the types of questions that we would ask competitors in order to determine a best solution. The first question is, how many total frames or total time is each person in the sequence for? And the second question is, how many total frames or total time is each person outside of the sequence for? The reason for creating these questions and data required to answer them is so that we can create metrics to measure and rank solutions and determine the best solution. It is also so that competitors know what types of data they need to keep track of. And these questions were designed so that the data required to answer them is machine readable and a metric to compare them can be created. Finally, I have made contributions to the team in assisting with the creation of our poster for the undergraduate research exposition and for the research paper itself. Our poster is shown here. The main part of the poster that I worked on was a future work section in which I described our plan for capturing the data, annotating it, and creating the competition. At the expo also, I went early to set up the poster and stayed the whole time presenting to around a dozen people. For the research paper, I've helped to write all of the sections, including the abstract, related work, introduction, and method. And that concludes his presentation. Thank you.